Alrighty, so today I'm going to be talking about Lab 3. I have the presentation for Lab 3, shear force and bending moment in beams. This is by myself, Nick Jones. So today we're going to be covering the experimental objectives, the theory behind the experiment, experimental procedures and equipment and how it works during the experiment, data and analysis of the data, as well as analysis of results and conclusions. So the experimental objective of this lab was for students to become familiar with calculating shear force and bending moment for an evenly distributed load on a cantilever beam. Strain gauges and direct measurements were used to determine the stress of the cantilever beam. So that is the experimental objective, kind of an overview of what this lab was supposed to do. So next, we're going to talk about the theory a little bit. So we have the theory behind the shear force diagram, and then we have the theory behind the bending moment diagram, and then next some equations to explain. But I'm going to talk about a little bit of it, and then we're going to go back and touch on those specific points. So for the theory, hang on 1 second. Can you go back to the first slide? Alrighty, so just to kind of look at that, the first theory slide. There we go. So you kind of look at the shear force diagram while I'm presenting. So shear force is the sum of all vertical forces acting on the beam. These forces can be applied forces or resultant forces. A shear force diagram is drawn to illustrate every point on the beam. The x-axis of a shear force diagram represents the length of the beam, whereas the y-axis represents the magnitude of the force. Bending moment is the sum of all moments on the beam due to vertical forces acting on it. A bending moment diagram illustrates the bending moment at every point on the beam. For this diagram, the x-axis also represents the length of the beam. The y-axis represents the magnitude of the bending moment. When determining shear force, and bending moment sign convention is highly important. It is very common to assume the vertical forces acting upward are positive, and bending moments acting in the counterclockwise direction are also going to be positive. This sign convention also applies when drawing the shear and bending moment diagrams. So the maximum moment obtained from the bending moment diagram can be inputted into what is called the flexure formula. In a little bit I'm going to kind of go over what that formula is. Now the flexure formula is to solve for the maximum stress, where sigma is the maximum stress and m is the maximum bending moment. And then c is the distance from the centroid to the outer surface, which we're going to kind of go over later. And then I is the moment of inertia. So once the maximum stress is found, we can use this other equation, which I will also go over later, that can be manipulated to solve for the maximum strain, where sigma is the maximum stress and E is Young's modulus. And then lowercase c I'll go over that later as well, is the maximum strain. So that's a little bit of theory behind the shear force diagram. Now to kind of recap a little bit, the shear force is the sum of all vertical forces. These are some of the important things that I wanted to highlight. So shear force is the sum of all vertical forces acting on the beam. A shear force diagram is drawn to illustrate the shear force at every point on the beam, and the x-axis of the shear force diagram represents the length of the beam, whereas the y-axis represents the magnitude of the force. This is kind of the key points of the shear force diagram. And then next, kind of some key points of the bending moment diagram. Bending moment is the sum of all moments on the beam due to the vertical forces acting on it. And then a bending moment diagram illustrates the bending moment at every point on the beam, as well as, and then we have X and Y conventions just like we did for the shear force. So, but for the bending moment diagram, for this diagram, the x-axis also represents the length of the beam. The y-axis represents the magnitude of the bending moment on the beam at every point. So that's kind of how we have that there. Could go to the next slide. And then these are those equations that I was talking about. So we have this equation, which is sigma mc, and then the moment of inertia, and then Young's modulus is equal to the strain divided by little e. So for the next slide, so these are kind of the experimental procedures. I do have it listed out here, but I'm not going to go through all of this. What I am going to do is I'm just going to kind of touch on it, go over some important points, and just kind of explain how the procedure in the experiment went, so we don't have to like sit here and read this. So what kind of happened is we had a cantilever beam, and we put X number of weights on the cantilever beam to see at certain measurements, at distinct measurements, to see exactly how that would affect the and create the bending moment and shear force diagrams all together. So that was kind of the experiment. So that kind of sums up all this in a short amount of time. So this was the equipment that we used. This was the cantilever beam, and we put in the next picture. This is kind of all the equipment, but in this picture, this is actually where the loads are applied to the cantilever beam. Here we have just 4, and there are certain measurements up here that so you can record where each weight is, and then we took measurements in recordings at 4, at 5, and then with 6 points of interest where there were weights. So that's kind of along the cantilever beam. So that's kind of the equipment that we use. In the next slide, we have the Wheatstone bridge display. So we had to figure out where to put these put these in the electrical circuit so that we were getting the correct readings from the cantilever beam. I believe in the first time that we tried this for this experiment, it was a little messed up, so we had to come back and fix it, and that was some points of error that I'll talk about later if we have time. But on to the next slide. So this is kind of the graph to explain, or not the graph, the table to explain some of the data that we had. So we did 3 different tests with, like I said, 4, 5, and 6 hangers. The weight for the hangers, each hanger was 0.3 kilograms, but it was just a matter of where we added it. So we added it consecutively along the cantilever beam in certain dimensions. So we have the weight per hanger, the total load, the force, and the displayed tensile strain, as well as the displayed voltage as recorded from the Wheatstone bridge display device. So on to the next slide. So this is kind of some of the hand calculations we did. Hand calculations of reaction forces, shear force diagram, and bending moment diagrams for the configuration with 4 hangers. So I just kind of wanted to give you an idea of some of the hand drawings that we did. That was submitted with the lab, and I'll also have this as a printout or a PDF to show you later if you want to refer back to it. So on to the next slide. So this is again, hand calculations of reaction forces, shear force diagram, and bending moment diagram for the configuration with 5 hangers. The previous one was 4 hangers. So it's just kind of displaying what happened or where the changes were. You can kind of go back and see later if you want to, where the changes were for the cantilever beam that's drawn, and then the shear force diagram, and then the bending moment diagram. So on to the next slide. And then this is hand calculations of reaction forces, shear force diagram, and bending moment diagram for the configuration with 6 hangers. So again, just the kind of generic drawing with the cantilever beam, and then you can see how the shear force diagram and the bending moment diagram are going to change with 4, 5, and 6 hangers. So next, this is going to be your free body diagram of the distributed load with 4 hangers. So the previous couple slides were showing how we did it with our hand calculations, and then this is actually how we used computer software to display what was going on as well. That way, we can kind of compare and see how we were doing with the hand calculations, as well as just kind of visualize how the computer did it. Get two different readings, like I said again, to check how we were doing it, and then as well, it makes it a little bit easier to read in kind of that aspect. So this was the free body diagram of the distributed load with 4 hangers, and then this slide was the distributed load with 5 hangers. So you can kind of tell the difference a little bit. Like I said, the numbers are here. They're a little bit small, so if you want to, you can go and refer later with the handout that I'm going to send out or include with this presentation. So here I have same thing, just 6 hangers, and numbers are small. You can see those later as well. This is going to be the shear force diagram, the distributed, specifically more up close, the shear force diagram of the distributed load with 4 hangers. So kind of describes what's going on there. Anything specific? And then this is the shear force diagram of the distributed load with 5 hangers. And then this is the distributed load of the shear force diagram with 6 hangers. This one is the bending moment diagram of the distributed load with 4 hangers. You can kind of tell there's a difference in the way that the bending moment, and the shear force diagrams are done. The shape changes a little bit because it's representing different things. So next we have the bending moment diagram of the distributed load with 5 hangers, and then the bending moment diagram of the distributed load with 6 hangers. And then the graphs do look the same, just because we're kind of working on the same, how do I say it, we're working on the same, like we're doing the same thing, we're just adding more, so we're changing, these numbers are changing. So this is the bending moment diagram with 6 hangers. And then the numbers were right here. We can go back to the slide real quick. So the numbers are right here. This is what's important. It goes down to negative 414.89, I believe that is. And then if you can go back one more time on the previous slide, it goes down to, here we have negative 68, I believe. Like, the numbers are hard to read. They're going to be on the slide or on the printout for later review. And then we go down to negative 323.66. And then going back one more slide. On this one we have, and then it goes down to negative 241.33. So then now if you want to go all the way to the conclusions. One second. So this is kind of what we found out. So the hand calculations, so what I wanted to explain from all that was that the hand calculations align with the shear force and bending moment diagrams calculated using the computer software. The results of the data obtained from the displayed values of tensile strain and voltage indicate that the distributed load was increased and that the displayed tensile strain and voltage would also increase. After the loads were removed, the displayed tensile strain would return to 0, thus indicating no permanent deformation was done to the cantilever beam. That's important in this experiment as well. So that is it, and then we'll also have so the percent difference for each of the 3 tests was close to 45%, which is a significant experimental error. This error was likely caused to the assumption of the cantilever beam dimensions based upon the equipment specifications. The assumption was made because there were no calipers to obtain accurate dimensions. So a few things I wanted to point out. The error in this experiment, a couple places the error came from. The error came from not being able to have the calipers, so we weren't able to get exact measurements along the cantilever beam to see exactly how far apart the weights were. And then also we weren't able to get a good ending and starting point because also we didn't have the calipers. So if we had the calipers, there would have been a much lower percentage of error than 45%. Also just human error of adding the weights and making sure they're exactly in the same spot on each weight in exactly the same difference. But calipers would have helped a lot. So with that being said, also I have the references, and the references, those are going to be on the on the next slide. And that's it. Thank you so much.